Hello and good evening to everyone, guys. I welcome you all once again to this wonderful channel by Unacademy NEET-English. Well, my name is Khurshid Alam and you can also call me KK sir. I hope you all are doing great. Before we move ahead, I want quick confirmation that if you can see me clearly and hear me clearly, let me know in the chats quickly. Let me know in the chats quickly. Let me know in the chats quickly. If you can see me clearly and hear me clearly, let me know in the chats. Let me know in the chats. Let me know in the chats quickly. Okay, I believe we are live now and super excited for today's session, which is on actually all naming reactions. Let me tell you, this session is very important, as around 4 to 5 questions in NEET 2026 will be directly from this session. So I would want you all guys to be with me till end. And I would want you all guys to mark the attendance by smashing the like button right now. So let me know in the chats, how is the Josh for today's session, which is going to be very important as per NEET 2026 is concerned. Let me know in the chats, how is the Josh, guys? How is the Josh? Come on, let me know. Let me know in the chats, how is the Josh? How is the Josh? Come on, each and everyone to respond, and I would want you all guys to be with me till end as we will kick off this session very nicely. Okay, this is very important session as per NEET 2026 is concerned. This is very important. Thank you, Harineep. Thank you, Nityasri. Thank you. Everyone, I would want everyone to show some Josh today. Come on. Anshika Sharma is saying hello. Hi, beta. How are you? Okay, come on. Lakshmir, Shabash, come on, Lakshmi, great. I would want all guys to be very much excited because this is the very important session. Come on. Approximately we are going to discuss 72 reactions today. I'm fine, beta, I'm fine, thank you. Hi. Hi everyone. But I would want you guys to be with me till end. Come on. Okay. So without wasting much more time, let's get going. So our first named reaction is it's Sabatier-Senderens reaction. So what is this? This is simply hydrogenation, reaction of alkenes, or this is hydrogenation of alkynes. I mean to say this is hydrogenation reaction of unsaturated unsaturated hydrocarbons. That means this is simply hydrogenation of unsaturated hydrocarbons taking place in presence of ordinary nickel. And that too at a temperature of 523 to 573 Kelvin. That means high temperature. At high temperature. Have a look. What you have to do is, you have to simply break this bond. You have to simply break this pi bond and you have to add hydrogen over here, hydrogen over here. Similarly, what you have to do is you have to break first pi bond, add hydrogen and hydrogen, then another pi bond, add another hydrogen and another hydrogen. That means here you need 2 moles of hydrogens. Here you need only 1 mole of hydrogen. So what will be the product? Product will be simply an alkane. Product will be simply an alkane. Here hydrogens will be added. And here once again product will be an alkane. But here 2 moles of hydrogens will be added. So that reaction during which unsaturated hydrocarbons are converted to alkane by adding hydrogens in presence of ordinary nickel at a temperature of 523 to 573 Kelvin is known as Sabatier-Senderens reaction. And remember forever, this reaction is used to synthesize. This reaction is used to synthesize Vanaspati ghee from edible vegetable oils. Now, let me know in the chats quickly, is this clear? Let me know in the chats, is this clear? Let me know quickly, is this clear? Because this is very easy reaction. What you have to do is only you have to break pi bond between 2 carbons and you have to add one hydrogen to each of these carbons. Similarly, you have to break 2 pi bonds and you have to add 2 hydrogens from one side and 2 hydrogen on another side so that we get alkane from this reaction. This is simply what we call a catalytic hydrogenation or catalytic reduction. But remember, catalyst used in this reaction is ordinary nickel, and this reaction takes place at high temperature. This is very easy reaction. Now, after that, and another reaction is that is Zerewitinoff's reaction. What is Zerewitinoff's reaction? Have a look. This is simply reaction of Grignard's reagent. Reaction of Grignard's reagent with any acidic hydrogen containing compound, say for example water. For example, you are having phenol, say for example HCl, say for example carboxylic acid, for example terminal alkyne, for example you can use ammonia, you can use primary amine. So these are the compounds which contain acidic hydrogen. That means they will simply release H positive. Their H positive will be accepted by this R of Grignard's reagent. Now when R positive accept or abstract hydrogen from these compounds, they will result in the formation of, so it will result in the formation of an alkane. So alkane will be the product over here formed by abstraction of hydrogen from these compounds by this R of Grignard's reagent. So here product formation will be an alkane. So that reaction of Grignard's reagent with any acidic hydrogen containing compound resulting in the formation of what we call alkane is known as Zerewitinoff's reaction. Side product will be negative part of this acid and MgX. Negative part of this acid and MgX. So that will be the side product of the reaction. Let me know, is this clear? This is a very important reaction, and that too a very easy reaction. I hope this is clear. So whenever Grignard reagent is treated with any acidic hydrogen containing compound resulting in the formation of alkane, reaction is known as Zerewitinoff's reaction. Another and a very important reaction is Wurtz reaction. Have a look. Very important reaction. This is very important reaction and very easy. First of all, you must know that this reaction is basically of 2 types. One is known as intermolecular and another is known as intramolecular. One is intermolecular, another is intramolecular. And this intermolecular reaction is of further 2 types. One is simple or self, and another is what we call mixed or crossed. So first of all, we will discuss this one, that is simple or self simple or self intermolecular Wurtz reaction. Intermolecular Wurtz reaction. Very, very, very important reaction. Have a look. This is very important reaction. What is this reaction actually? This reaction is actually of alkyl halide and sodium. This is reaction of actually alkyl halide and sodium in presence of dry ether. Intermolecular means between the molecules this reaction will take place, and when it is simple or self, that clearly indicates that alkyl halide which undergoes intermolecular Wurtz reaction, both those molecules of alkyl halide must be similar. That means there is self or what we call reaction or reaction taking place between similar alkyl halides. So what is the trick over here? What you have to remember is break carbon halogen bond when it is treated with what we call sodium and result in the formation of a radical. Once a radical is formed, then coupling of this radical will take place or combination of this radical will take place, and combination of this radical takes place with same type of radical in case of simple or what we call simple or self intermolecular Wurtz reaction. Coupling of similar radical will take place and it will result in the formation of alkane. Okay, now remember. So here generally symmetrical alkanes are obtained during this reaction. For example, if we take an example of CH3Br and it's undergoing simple intermolecular Wurtz reaction, what we have to do is just break this bond, form a radical, combine it with similar type of radical, so your product will be like this. Similarly, if you are having CH3CH2Cl in presence of dry ether and sodium, just break this bond, it will result in the formation of CH3CH2 radical, and then this CH3CH2 radical will combine with similar type of radical and it will give us an alkane. So what you have to remember is that methane cannot be obtained. Methane cannot be obtained during this reaction, because Wurtz reaction, normal Wurtz reaction is basically a combination reaction. So there will be no formation of methane at all. Another is that tertiary alkyl halides generally do not show this reaction. Now, after that, if you are having a mixed or crossed intermolecular Wurtz reaction, mixed or crossed intermolecular Wurtz reaction, what is meant by that? That means once again an alkyl halide undergoes Wurtz reaction, but here alkyl halides will be different. That means different alkyl halides, say for example Rx and R'X will undergo Wurtz reaction. So under Wurtz condition, that means on treatment with sodium and dry ether, what will happen over here? First of all, you have to break this bond, a radical is formed. Similarly, break this bond and a different radical is formed because R is not equal to R prime. Here two different radicals are formed, hence possibility of combination of two different radicals will be like this. R will combine with R radical, R prime will combine with R prime radical, or R can combine with R prime radical. That means we can get R prime, and R prime. But remember, all these, alkanes are obtained in this reaction in a mixture. That means this, all are present in impure form. But this alkane which is obtained by combination of similar radicals, or this alkane which is obtained by combination of similar radicals R prime and R prime, can be obtained in pure form in Wurtz reaction like this. Can be obtained in pure form like this. R radical will combine with R radical, RR can be formed, or R prime radical can react with R prime radical. It can be resulting in the formation of RR and R prime in pure form. But remember, this alkane which is obtained by combination of, R radical and R prime radical. I mean to say, combination of different radical is always obtained in impure form. What does that mean? That clearly indicates such type of alkane cannot be prepared in pure form during Wurtz reaction. Hence, we can simply say Wurtz reaction is not the best method, to prepare R prime. That means it's not best method to prepare that alkane which is obtained by combination of different what we call radicals. But instead of that, Wurtz reaction is considered best method to prepare those alkanes which are prepared by combination of same radicals. That means Wurtz reaction can be a best method to prepare RR or R prime alkanes. In general, Wurtz reaction is considered as best method to prepare symmetrical alkane, but Wurtz reaction is not considered as best method to prepare unsymmetrical alkane. For example, if we take an example of mixed or crossed intermolecular Wurtz reaction, say for example like this, CH3Br and CH3Br. If we take two different alkyl halides in Wurtz reaction, what will happen? Have a look. First of all, break this bond and form a radical. Similarly, break this bond and form a radical. This radical can combine with similar radical and results in the formation of this one. Similarly, this can react with another same radical and can result in the formation of this one. But when we combine these two different radicals, then product will be like this. So this is the product which is obtained only in impure form, because this is formed by two different radicals. But this product can be prepared in pure form, like if I take only CH3Br and treated that with sodium and dry ether, this can be formed. Similarly, if I treat only isopropyl bromide with sodium, this can be prepared in pure form, but this cannot be prepared alone. Whenever this is prepared, it is prepared with these alkanes as well. So Wurtz reaction is considered as best method to prepare symmetrical alkanes. It is not considered as best method to prepare unsymmetrical alkanes, or in nutshell, alkanes which are prepared by combination of different radicals. After that, we are having intramolecular Wurtz reaction. In this, what will happen? Reaction takes place within the same molecule. Say for example, we are having like this. we are having a structure like this. This is Br, this is Br. Now what will happen in presence of sodium or under what we call Wurtz condition? What will happen? It will result in the formation of a radical first. Bond will break, it will result in the formation of a radical first. Then this radical and that radical will combine and it will result in the formation of this. Similarly, if we are having a structure like this, here it is Br, here it is Br. Now, after this, when this is treated with sodium and dry ether, what will happen? This bond will break. Now, it will result in the formation of a radical over here. This bond will break, it will result in the formation of a radical over here. Now, have a look, this is 1, 2, 3 and 4. That means 1, 2, 3 and 4. 4 and 1 will combine and they will result in the formation of a 4-membered ring. So, this is 1, 2, 3 and 4. 4-membered ring will be obtained. That means this is intramolecular Wurtz reaction. Let me know in the chats. Let me know in the chats. Is this clear? Am I clear till now? Am I clear till now? Let me know in the chats. Let me know in the chats quickly. Let me know in the chats quickly. Come on. Come on. My dear lovely students, let me know in the chats. Aditya, thank you. Pavana, thank you. Nityasri, thank you. Thanks for replying. Harshi, thanks. At the rate of Sisi, yes, thank you. Rivka, God bless you. Thank you. Pavana, super clear. Thanks a lot. Thanks for responding. God bless you all. So, after that we have what we call a Fittig reaction. Wurtz reaction was alkyl halide and sodium. Reaction of alkyl halide and sodium resulting in formation of generally symmetrical alkane. Now, what's Fittig reaction? Fittig reaction is simple. Very simple. It is reaction of aryl halide. It's reaction of aryl halide with sodium in presence of dry ether. What you have to do is simple. Same trick like that of Wurtz. Just break this bond, form a radical over here. This is the trick. Form a radical over here and combine this with similar type of radical. That means you will get a biaryl species like this. So whenever aryl halide undergoes reaction with sodium and dry ether resulting in the formation of biaryl, we can simply call that as Fittig reaction. This is very easy. After that, Wurtz-Fittig reaction. That means it is combination of Wurtz and Fittig. What was Wurtz? Wurtz was a reaction of alkyl halide with sodium and Fittig is reaction of what we call aryl halide with sodium. That means whenever both alkyl halide and aryl halides are treated with sodium in presence of dry ether, what will happen? This bond will break, so it will result in the formation of a radical. Similarly, this bond will break, it will result in the formation of a radical. After that, what will happen? This radical can combine with another radical. That means RR can be formed. This radical can react with another phenyl radical. That means biphenyl or biaryl can be obtained. But another possibility is this R will combine with this. That means alkyl benzene can also be obtained during this reaction. Am I clear? But this is the major product. That's why we can simply remember that whenever alkyl halide and aryl halide reacts, alkyl benzene will be obtained. Now, let me know in the chats, am I clear till now? Am I clear till now? Let me know in the chats. Okay, as light has gone, so let me switch off some, light so that our energy, power energy will be consumed, will be saved. Okay. Let me know in the chats. Let me know in the chats. Am I clear till now? Am I clear till now? Come on. Asha. Thanks, beta. Thanks for replying. Sankit Mani. Thanks for replying. Pavana. Kirti. Okay. Rivka. God bless you. Ruth. Come on, come on. Okay. Okay. Great. Thank you everyone for responding. Now, after that, we have another reaction, that is Ullmann biaryl synthesis. What is Ullmann biaryl synthesis? It is actually simply reaction of iodobenzene in general. Reaction of iodobenzene in general with, copper. This reaction is taken place finally in a sealed tube and we will heat it. And similar type of reaction will take place. This bond will be broken and a phenyl radical will be obtained. This phenyl radical will combine with another same type of radical and it will result in the formation of what we call biphenyl. So whenever iodobenzene is treated with copper and it will result in the formation of biphenyl, this is known as Ullmann biaryl synthesis. After that, we have another reaction, that is Frankland's reaction. What is Frankland's reaction? Have a look. Whenever you are having what we call an alkyl halide and that is treated with zinc, it first results in the formation of dialkyl. It results in the formation of dialkyl zinc, like this. This is known as Frankland's reagent. This is known as Frankland's reagent. That means to balance the reaction, I will write down this as twice. After that, it will become, this is twice, then it is ZnX2. So this is balanced. After that, this, say Frankland's reagent will react with alkyl halide. That means alkyl halide is taken in excess. When it reacts with this, a sort of SN2 reaction is there. Say whenever zinc is attached to carbon, carbon is more electronegative as compared to metal. This will act as a nucleophile, it will attack and X will be lost. So it will result in the formation of RR, once again a symmetrical alkane. Once again a symmetrical alkane is obtained, plus it will be RZN, okay, then X minus will be lost. So let me write down only main product, that means symmetrical alkane. So that reaction in which Frankland's reagent reacts with alkyl halide resulting in the formation of symmetrical alkane is known as Frankland's reaction. So trick for this is like this. Whenever you have alkyl halide, say CX bond is there and zinc is there. So just do one thing, just remove this, say break this bond, form a radical. Radical is not formed over here, but you just, this is a trick, form a radical and combine that radical with similar type of radical, your alkane will be obtained. So this is what we call Frankland's reaction. After this, we have another reaction, that is Kharasch's reaction. What is Kharasch's reaction? Remember, whenever you have alkyl halide reacting with lithium, it first results in the formation of alkyl lithium and lithium halide. That means lithium should be, say twice. After that, this RLI reacts with CuI and it will result in the formation of RCu, R and Li. This is known as lithium dialkyl cuprate, known as Gilman's reagent. Known as Gilman's reagent. For this, you have to write down this twice. After that, it is Li and I, lithium iodide. After this, this Gilman's reagent will react with alkyl halide. This alkyl halide, now this Gilman's reagent will attack on this alkyl halide. That means a normal SN2 reaction takes place, X will be lost. Then the product will be R prime. Then RCu, that means alkyl copper will be there and lithium halide will be there. This can be symmetrical or it can be unsymmetrical alkane. Now have a look. During Wurtz reaction, symmetrical alkanes were prepared in pure form. That means that was best method to prepare symmetrical alkane. Frankland's reaction is also best method to prepare symmetrical alkane. But this reaction, during this reaction, you can prepare symmetrical as well as unsymmetrical alkane. So we can simply say, to prepare unsymmetrical alkanes, as we know, Wurtz reaction is not a good method to prepare unsymmetrical alkanes in general. Neither Frankland's reaction is a good method to prepare unsymmetrical, alkane. That's why to prepare unsymmetrical alkanes, Kharasch's reaction is preferred or Wurtz reaction. So remember this point as well. So what is Kharasch reaction? In one line, we will simply say reaction of Gilman's reagent with alkyl halide resulting in the formation of either symmetrical alkane or unsymmetrical alkane is known as Kharasch reaction. And this is considered as better method to prepare unsymmetrical alkane over say Wurtz reaction. I hope this is clear till now. Let me know in the chats. Am I clear till now? Am I clear till now? Am I clear till now? Let me know in the chats quickly. Let me know in the chats quickly. I am waiting for your response. Come on. Let me know in the chats quickly. Thank you, Aditya Gopala, for responding. Thank you. Asha, thank you. Rifka, thanks for replying. Venkataramana. Okay, thank you. Ceci, thank you. Thank you very much. Thank you, everyone. Now, after this, we are having awkward process. What is awkward process? Let me write down over here. It is decarboxylation of carboxylic acid. Decarboxylation of carboxylic acid by using soda lime. What is soda lime? NaOH and CaO in the ratio of 3:1 is known as soda lime. Have a look. First of all, if we are having an acid on treatment with, say for example, a base will simply abstract this hydrogen and we will get sodium salt of carboxylic acid or sodium carboxylate. Now, this will undergo a reaction like this. It will simply results in the formation of R having negative charge. That means a carbanion will be obtained. To that, Na positive will attract and carbon dioxide will be, carbon dioxide will be formed. This step is the slowest step of the reaction or rate determining step of the reaction. That means, so rate of decarboxylation by using soda lime is actually what we call simply dependent on stability of carbanion, and this reaction takes place in presence of NaOH, CaO and heat. That means in presence of soda lime. After that, this carbon dioxide will react with NaOH and finally we will get, decarboxylation will take place and we will get Na2CO3 here plus H2. And then this R negative, carbanion will abstract hydrogen from water and it will result in the formation of an alkane plus NaOH. NaOH is basically a catalyst. One of the NaOH will act as a catalyst. So, rate of decarboxylation here is directly proportional to stability of carbanion formed in RDS. Remember this is very, very important point. Remember this one. Okay. Say for example, you are having now RCOOH or you are having RCOONA and you want to perform what we call a decarboxylation reaction by using NaOH, CaO at high temperature. What you have to do is just break this bond or this bond and form what we call a carbanion over here. Once carbanion is formed, it will abstract H, so the product will be this. For example, if you are having CH3COOH, then what will be the product? Product will be simply break this bond, CH3 minus will be formed, it will abstract H positive, so the product is methane. Similarly, if you are having this one, COONA or COH, break this bond, carbanion is formed and then it simply results in the formation of cyclohexane. So this is very, very, very simple reaction. But have a look. If you are having a question like this, that you have to tell rate of decarboxylation. You have to compare rate of decarboxylation. Suppose we have to compare rate of decarboxylation. One acid is like this and another acid is like this. What you have to do is you have to remove this COH or CONA and form a carbanion over here. Similarly, remove this, form a carbanion over here. That means when you break this CCOH bond, this carbanion will be obtained, and here this carbanion will be obtained. This is an anti-aromatic compound, highly unstable. This is aromatic, highly stable. Have a look. Rate of decarboxylation is directly proportional to stability of carbanion formed in RDS. That means we know this carbanion is more stable as compared to this. So this carbanion has been formed from this. Hence, rate of decarboxylation will be simply 2 greater than 1. Now, let me know in the chats, is this clear till now? Am I clear till now? Let me know in the chats. Great, great. Asha, very good. Satya, very good. Satyam the Great, very good. Very good, very good, very good. So, duration. It will be approximately 3 hours, most probably. Or it can be 3 hours, 10, 15 minutes. Or it can be less than, say 3 hours by 10 minutes. That means it can be around 2 hours 45 minutes to 3 hours 15 minutes. Okay, that's great. That's great. That's great. Now, after this, we have another reaction, a very, very, very important reaction, Kolbe's electrolysis. This is once again a decarboxylation reaction. This is once again a decarboxylation reaction. This is a decarboxylation reaction of carboxylic acids. Once again, but by using let me know in the chats, guys. Let me know in the chats. Am I visible and audible? Am I audible and visible? Let me know in the chats, guys. Let me know in the chats. Am I audible and visible? Let me know in the chats. As there was some issue in my internet, let me know if issue has been resolved or not. Please let me know in the chats. Is issue resolved? Am I audible? Okay, 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 okay. Thank you, thank you, thank you, thank you. So, Kolbe's electrolysis, let me repeat this one. Kolbe's electrolysis is basically what we call a decarboxylation reaction of, this is decarboxylation reaction of carboxylic acid. This is decarboxylation reaction of carboxylic acid by using electrolysis. What you have to do is either sodium salt or potassium salt is of acid is treated with water, and you have to perform electrolysis of that. First of all, you just break this carbon and R bond and form R radical. Then combination of this R radical will take place and alkane will be obtained at anode. Carbon dioxide gas will be evolved at anode. Hydrogen gas will be evolved at cathode, and in solution there will be NaOH or KOH. That clearly indicates that what we call solution is basic. That means pH of solution will be greater than 7. After that, you have to remember this very, very important point, that if value of R is H, that means RCONA at that time becomes HCONA. So if R is H, this R is H, at that time we will get H2 gas at anode carbon dioxide gas, and H2 gas at cathode as well. That means we will obtain hydrogen at anode as well as cathode, and carbon dioxide at anode, and solution will be either NaOH or KOH. That means pH of the solution will be greater than 7. I hope this is clear till now. Am I clear till now? Let me know in the chats quickly. Let me know in the chats quickly, my dear students. Let me know. Let me know in the chats. Let me know in the chats quickly. I'm waiting for your response. Come on, quickly. Let me know in the chats. Okay, Aditya Gopala, thank you very much. Okay, Sisi, thanks. Asha, thanks. Kirtana, thanks. Maria, thanks. Asiba, thanks. Hershey, thanks for responding. Rivka, thanks for responding. Okay. Hershey, thanks. Okay, God bless you all. Now after this, we have another reduction, that is Birch reduction. But in our syllabus, we are having only partial reduction of alkynes. We have partial reduction of alkynes and partial reduction of alkynes by using sodium in liquid ammonia, or you can use lithium in liquid ammonia. Now, what is the reaction? Have a look. If you are having an alkyne like this, you have to reduce this alkyne. You have to reduce this alkyne by using either sodium in ammonia or by lithium in ammonia. Now have a look what will happen over here. You have to break, simply, you have to break one pi bond and you have to add hydrogens. But remember, on adding hydrogen, it will result in the formation of an alkene. And if this alkene can exist in cis and trans form, then here we will get a trans alkene. We will get a trans alkene over here. And reaction will stop. That means this is partial reduction of alkyne to trans alkene. So this is known as Birch reduction. After that, we have Kharasch's effect. Kharasch's effect is also known as peroxide effect. It's also known as peroxide effect. Have a look. If you are having an unsymmetrical alkene, say for example propene, and we want to add HBr, unsymmetrical reagent, to this, in presence of peroxide, say for example benzoyl peroxide, then what will happen? Addition of this HBr takes place according to anti-Markovnikov's rule. That means negative part of this addendum goes to that carbon-carbon double bond which was having lesser number of hydrogen. That was Markovnikov's rule. But you have to add according to anti-Markovnikov's rule. That means you have to add negative part here and positive part here. But remember, it's not basically Br minus which has been added. It's not basically H positive which has been added, as this reaction is an example of free radical addition reaction. This is an example of free radical addition reaction. But remember, intermediate of this reaction is a carbon free radical. Intermediate of this reaction is free radical. But the product formation is always anti-Markovnikov's product. So you have to remember these points. Now, after this reaction, we have another reaction known as ozonolysis. Ozonolysis is of two types. One is known as reductive ozonolysis, and another is known as oxidative ozonolysis. Here reagents are generally ozone and zinc, or zinc H2O, or what we call dimethyl sulfide, or triphenyl phosphine. Here it's ozone, and number second reagent, is either water or H2O2. Have a look. If you are having an alkene like this, what you have to do if you perform reductive ozonolysis? Have a look. Just break this bond and form double bond O over here, double bond O over here. That means your product is like this. This is reductive ozonolysis. But if same alkene undergoes oxidative ozonolysis, then have a look. It's O3, then second it's H2O2. What you have to do is break this bond and that carbon which is having two hydrogens attached to this, that means carbon, double bonded carbon having two hydrogens attached to that double bonded carbon, you have to simply convert this into carbon dioxide and water. And if this double bonded carbon is not having any hydrogen, then convert it into ketone. That means the product of this reaction will be simply one as ketone, because this carbon, double bonded carbon, is not having any hydrogen. This is having two hydrogens. If it is having two hydrogens, convert it into carbon dioxide and water. If it is having only one hydrogen, then convert that CH bond into COH like this. Have a look. Have a look. If you are having this one, CH3C, CH3, double bond C, CH3 and H, reductive ozonolysis upon, say O3, number second, zinc water. What you have to do is just break this bond, add double bond O over here. So the product of this reaction will be like CH3, CH3, double bond O plus it will be O double bond C, CH3 and H. But if same alkene undergoes oxidative ozonolysis, if same alkene undergoes oxidative ozonolysis, what will happen over here? Have a look. Have a look. Just break this bond. This carbon is having one hydrogen. Just convert this into COOH. CH3 is there, so it becomes CH3COH. But this carbon does not have any hydrogen, so convert this into ketone. I mean to say product will be like CH3 double bond O plus CH3 COOH. Because when carbon is having one hydrogen, convert CH into COH and remaining part will be attached to COH. But if carbon is having two hydrogens, then convert this into carbon dioxide and water simply. If it is not having any hydrogen, then convert it into ketone for oxidative ozonolysis. But for reductive ozonolysis, whether carbon is having one hydrogen, two hydrogen, or carbon is not having any hydrogen, just break the bond and give double bond O to both these carbons which were joined together by means of a double bond. I hope this is clear till now. Let me know in the chats. Let me know in the chats. Is this clear till now? Is this clear till now? Quick. Quick, 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 quick. Because this will help you a lot in revisions. Come on, let me know in the chats. Am I clear till now? Am I clear till now? Waiting for your response. Waiting for your response. Aditya Gopala, thanks. Asad Ali Khan, thanks. Asiba, thanks. Sisi, thanks. Maria, thanks. Great, 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 great. Okay, Omihania, thanks. Kithana, thanks. Okay, nice. After this, we have another reaction, that's hydration of alkenes. Now have a look. This is actually addition of water. Hydration means addition of water. Addition of water to alkenes. To alkenes. In presence of acid. That means it is acidic in presence of protonic acid. Say for example in presence of H2SO4 or H3PO4. I mean say in presence of protonic acids, that acid which can donate H positive. That means if we are having an alkene like this, when it is treated with, I mean to say H2O, when it is treated with H2O in presence of acid, what will happen over here? Here addition will take place according to Markovnikov's rule, or addition will take place via more stable carbocation. I mean say product of this reaction will be this. Have a look how. You have to remember mechanism for this reaction, because intermediate is carbocation. Whenever carbocation is an intermediate, rearrangement can take place. So it is like this. It is RCH double bond CH2 then plus HOH and H, because here this acid and water will combine and results in the formation of hydronium ion. After this, in presence of this H positive, first step is simply protonation of alkene. First step is simply addition of proton to alkene. When alkene, I mean say proton is added to alkene, we will get a carbocation. we will get a carbocation. Now, rearrange if possible. If carbocation can rearrange, if carbocation after rearrangement forms more stable carbocation, rearrange. That's why we will write rearrange if possible. After that, once this carbocation is there, finally, nucleophile will attack. That means water will act as a nucleophile and it will attack to this carbocation and it will result in the formation of this one, OH with a positive charge. Finally, this will, I mean to say, this product of second step will lose proton. That means deprotonation will take place. In first step, it is protonation. In second step, or formation of carbocation. In second step, it is attack of nucleophile on carbocation. And in third step, it is deprotonation and it will result in the formation of this product, which is known as alcohol. I hope this is clear. After that, we are having another reaction, a very, very important reaction known as hydroboration-oxidation. Now, generally hydroboration-oxidation, Oxymercuration-demercuration and ozonolysis, they are very important for alkenes, but these reactions can also take place in alkynes. But I will show here hydroboration-oxidation, that means indirect hydration. This is also an indirect hydration. It can be of alkenes or alkynes, but I will show indirect hydration of alkenes over here because alkenes are very important. Now, have a look. Whenever you are having an unsymmetrical alkene, and reagent is like this, B2H6, I mean say diborane, and the solvent is THF, or at instead of THF, heat is there. After that, it is H2O2 in basic medium. Whenever you see, I mean say this type of reagent, add water across either double bond or triple bond. Here it is double bond, so I will write down across double bond according to anti-Markovnikov's rule. That means negative part of water should go to this carbon which is having more number of hydrogens across carbon-carbon double bond. So the product will be like this. Across carbon-carbon double bond, negative part will go over here, positive part will go over here. Okay. This reaction is also a syn addition reaction. Remember, this is an example of syn addition reaction. After this reaction, we have Oxymercuration-demercuration reaction. This is also an indirect hydration reaction. Indirect hydration reaction of alkenes or alkynes. So indirect hydration of alkenes or alkynes. Let me show alkenes over here. Once again, RCH double bond CH2 on treatment with, whenever it is treated with mercuric acetate and H2O, number one. Number second, it's treated with NaBH4 OH negative. Whenever you are having this type of reagent, just add water across carbon-carbon double bond or carbon-carbon triple bond, depending upon here whether it is alkene or alkyne. As here it is alkene, so across double bond you have to add water according to Markovnikov's rule. What was Markovnikov's rule? Negative part of water, that means negative part of molecule to be added. Negative part goes to that carbon-carbon double bond which is having lesser number of hydrogens. So we will add negative part over here and positive part over here. So I hope this is clear till now. So am I clear till now? Am I clear till now? Am I clear till now? Let me know in the chat quickly. Am I clear till now? बेटा जब किस्मत में होगी तब अनअकैडमी JNK भी आ सकते हैं, लेकिन जरूरी नहीं है कि उस पे मैं आऊं ना. Okay, so this is clear. Thank you, thanks for responding. Okay, now then it is Kucherov's reaction. What is Kucherov's reaction? It is simply addition of water to alkynes. Addition of water to alkynes. It is simply addition of water to alkynes. Now have a look. If you are having an alkyne like this and we want to add water, reaction generally takes place in HgSO4 and dilute H2SO4 at a temperature of 333 Kelvin. What we have to do is just have a look. Add water across carbon-carbon triple bond according to Marconi-Kopp's rule. You just break one pi bond and add OH to that carbon-carbon triple bond, negative part of water to that carbon-carbon triple bond which is having lesser number of hydrogen, and positive part to that which is having more number of hydrogen. In nutshell, we will obtain an enol over here. This is known as enol. Then this enol will undergo tautomerization and it will result in the formation of a keto product like this. So this is what we call Kucherov's reaction. After this, we have Friedel-Crafts alkylation reaction. Now have a look. Say for example, we are having an aromatic compound and after that, we react it with alkylating agents. Have a look. Alkylating agents. Alkyl group is introduced in benzene ring. This is known as Friedel-Crafts alkylation reaction. Now, the question is, what are alkylating agents over here? Here, we can use either RCl in presence of Lewis acid. At that time, carbocation or alkyl carbocation can be formed as an electrophile. And as here carbocation is having complete positive charge, so rearrange if possible. So rearrange if possible. First rearrange this if possible. After that, add that R positive to benzene ring. Okay. Now similarly, if alkyl chloride is treated with FeCl3, then electrophile of this reaction will be like this: RClAlCl3 having partial negative charge, partial positive charge. As this carbocation is having partial positive charge, so there will be no rearrangement at all. Then what you have to do is, whatever the value of this R is, put that R to this or add that R to this, say benzene ring or aromatic ring. After that, if you are having an alkene, say for example this one, and you are having an acid, first of all these two will combine and they will result in the formation of a carbocation. Once carbocation is obtained, you have to check whether that carbocation undergoes rearrangement or not. That means you have to check rearrangement. So rearrange if possible. Rearrange if possible. After that, fourth one is alcohol in presence of H positive. So once again, you have to form R positive over here and rearrange if possible. Rearrange if possible. Rearrange if possible. Now, after that, when you simply rearrange first, third and fourth, a stable carbocation will be obtained. After that, carbocation will be attached to this and in the form of alkyl group. Here, there will be no rearrangement, but in first, third and fourth, there will be rearrangement. This is known as Friedel-Crafts alkylation reaction. After that, we are having Friedel-Crafts acylating or Friedel-Crafts acylation. Have a look. For example, you are having a benzene ring. After that, you want acylation, that means introduction of acyl to benzene ring. Acyl is this one, C double bond O and R. You want to introduce acyl, and remember this is possible only in presence of acylating agents. And remember, acylating agent here are either acyl chloride in presence of Lewis acid, say for example AlCl3, and here carbocation will be like this, but there will be no rearrangement as this carbocation is stabilized by back bonding. There will be no rearrangement. That means you have to add this C over here, C double bond O and R. Acyl group will be introduced. Or Second can be anhydride. Second can be anhydride in presence of once again AlCl3. And once again reagent, electrophile will be same. So this is Friedel-Crafts acylation reaction. But before moving forwards, let me know in the chats. Am I clear till now? Am I clear till now? Let me know in the chats quickly. Let me know in the chats quickly. Am I clear till now? Let me know in the chats quickly. Am I clear till now? Okay, thank you. Thanks for responding. God bless you all. After that, we are having Darzens halogenation reaction. This is also known as Darzens procedure. This is also known as Darzens procedure. So what is this? This is simply reaction of alcohol with SOCl2, say thionyl chloride. What you have to do is you have to form RCl, SO2 and HCl as the products. So here it is RCl, then it is SO2, then it is HCl, which will be the products over here. But remember, as SO2 is a gas, HCl is a gas, byproducts are gases. That's why we can simply use this reaction by replacing OH with Cl, and remember this reaction is considered as best method. This reaction is considered as best method to prepare RCl from alcohol. After this, we have another reaction, that is Finkelstein reaction. This is a halogen exchange reaction. This is a halogen exchange reaction. During this reaction, alkyl chloride or alkyl bromide on treatment with sodium iodide or potassium iodide. So sodium iodide or potassium iodide, that means alkyl chloride or alkyl bromide is treated with sodium iodide or potassium iodide in presence of dry acetone. This is an SN2 reaction. What will happen? This replacement or halogen exchange will take place, and in this dry acetone, this is soluble, this is also soluble. So I minus will replace Cl, here I minus will replace Br. That means we will get alkyl iodide over here. But if we take NaI, then NaCl will be obtained. If we take Ki, then KCl will be obtained in first reaction. And this NaCl or KCl is, insoluble in dry acetone. It will be, precipitated and it will come out of the solution. After this, here it will be NaBr, which will, be precipitated and it will come out of the solution. Hence, this reaction is favored by Le Chatelier's principle as well. After that, we are having another reaction, that is Schwartz process. Once again, a halogen exchange reaction. Halogen exchange reaction. But here, what will happen? Either alkyl chloride or alkyl bromide, it is treated with inorganic fluorides, but those inorganic fluorides which are heavy metal fluorides. That means with heavy metal fluorides, remember, like AgF, like HgF2, like Hg2F2, like SbF3, like AsF3, like COF3, etc. So these are the basically heavy metal fluorides which are generally used in this reaction. What will happen? Here, simple halogen exchange reaction will take place. Cl will be replaced by F. Similarly, Br will be replaced by F. That means with the help of this reaction, we can get, alkyl fluoride from either alkyl chloride or alkyl bromide. And here, this AgCl will be precipitated out, so that reaction will prefer in forward direction. Similarly, AgBr will be precipitated out and comes out of the solution, and reaction will prefer to move forwards. After that, we are having another reaction, very important reaction, and that is Sandmeyer's reaction. Sorry, what is Sandmeyer reaction? Benzene diazonium chloride on treatment with either Cu2X2 or Cu2X2 in presence of HX or CuXHX. But remember here X is either Cl or Br. Then it will replace this N2. It will replace this N2 and will result in the formation of either chlorobenzene or bromobenzene. So what is Sandmeyer reaction? In this reaction, we will get chlorobenzene or bromobenzene on treatment with cuprous halide in presence of HX or cuprous halide and HX. This is very simple reaction. After that, Gattermann reaction. Once again, it's a modified Sandmeyer reaction like this. Benzene diazonium chloride on treatment with, instead of cuprous halide, here it is copper powder and HX. This N2 will be replaced by X. That means here as X is Cl or Br, once again during Sandmeyer reaction as well as in Gattermann reaction, product will be chlorobenzene or bromobenzene. But remember, yield of this where X is either Cl or Br, that means chlorobenzene or bromobenzene, is more in Sandmeyer's reaction as compared to Gattermann's reaction. So can I say to prepare chlorobenzene or bromobenzene from benzene diazonium salt, Sandmeyer reaction is preferred as compared to Gattermann reaction. After that, we are having Balz-Schiemann reaction. What is this? It's basically when you are having a benzene diazonium chloride on treatment with HBF4, negative or anions, an anion exchange will take place and it will result in the formation of benzene diazonium tetrafluoroborate, which upon heating will simply lose this N2 and will result in the formation of fluorobenzene. This is known as Balz-Schiemann reaction. So here nitrogen is also, evolved. So this is Balz-Schiemann reaction. After this, we are having Dow's process. What is Dow's process? It is simply a reaction of chlorobenzene in presence of sodium hydroxide, reaction of chlorobenzene with sodium hydroxide at a temperature of 623 Kelvin and at a pressure of 300 atmospheres. Here NaCl will be lost, water will be lost, and it will first result in the formation of sodium phenoxide, which upon acidification, say for example HCl dilute, will result in the formation of NaCl will be lost and it will result in the formation of phenol. So whenever we are having a reaction of chlorobenzene with sodium hydroxide at 623 Kelvin and 300 atmospheric pressure followed by acidification, we will get phenol. This reaction is known as Dow's process. After that, Lucas test. Remember, what is Lucas test? It is basically the test with the help of which we can distinguish primary alcohol, secondary alcohol and tertiary alcohol. It's a test with the help of which we can distinguish primary alcohol, secondary alcohol and tertiary alcohol. By using Lucas reagent. What is Lucas reagent? It is HCl and anhydrous zinc chloride in the ratio of 1:1, but at room temperature. Remember here, no turbidity appears. But here turbidity appears. That means product formation takes place. Turbidity appears because of formation of product. What will be the product? OH will be lost, and instead of OH, this Cl will, replace this OH. That means here CH3, CH, CH3, Cl, isopropyl chloride will be the product. So turbidity appears after 5 to 10 minutes. Here turbidity appears, product formation takes place very quickly. So turbidity appears immediately. That means turbidity appears in seconds. So that means tertiary alcohol is very reactive as compared to secondary, as compared to primary alcohol. So this is what we call Lucas test, which can distinguish primary, secondary and tertiary with the help of Lucas reagent. Because if we are having an alcohol in a test tube, but we don't know which type of alcohol is this primary, secondary or tertiary, we will add Lucas reagent at room temperature. If turbidity appears immediately, then we can simply say this alcohol is tertiary. If turbidity appears after some time, after 5 minutes, 10 minutes, we will say this is secondary alcohol. If turbidity does not take place or it take place after hours, we can simply say this is a primary alcohol. So this is Lucas test. After that, we are having Victor Mayer's test. Have a look. Suppose we are having a doubt that whether a test tube contains 1 degree, 2 degree or 3 degree alcohols, then we can simply use this test which can distinguish this primary, secondary or tertiary alcohol. But what we have to do is, we have to add, number one, we have to add iodine in presence of red phosphorus. Number second, we have to add, remember, AgNO2. After that, we have to add HNO2. And lastly, we have to add aqueous NaOH. So, observation will be like this. There will be a blood red coloration or red color. Or there will be a what we call blue coloration taking place at the end of the reaction. Or at the end of the reaction, solution will be colorless. If it is red color, then remember our alcohol was primary alcohol. If it is blue color, then our alcohol was secondary alcohol. If it is colorless, then our alcohol was tertiary alcohol. And remember, this test, because of red, blue and this colorless, is also known as RBC test. So this test can be used to distinguish 1 degree, 2 degree and 3 degree alcohols. After this, we are having Hunsdecker reaction. What is meant by this? That means whenever silver salt of carboxylic acid is treated with bromine and then refluxed in an inert solvent, like CCl4. Now here decarboxylation will take place and it will result in the formation of alkyl bromide. Decarboxylation will take place, results in the formation of alkyl bromide and AgBr. This is known as Hunsdecker reaction or Borodine-Hunsdecker reaction. Similarly, if we use B instead of Br2, if we use Cl2, then product will be RCl. But if we use I2, then instead of alkyl iodide, product formation will be, instead of alkyl iodide, product formed will be an ester. Product formed will be an ester. Ester will be formed and then carbon dioxide will be evolved. That means once again a decarboxylation reaction is this, and after that we will get AgI. Now have a look. Ag is balanced, I is balanced. We are having 4 oxygens over here. Here we are having 4 oxygens. R2, R is balanced, carbon is balanced. This reaction in which when silver salt of carboxylic acid is heated with or refluxed with iodine, resulting in the formation of ester instead of alkyl iodide, is known as Bin-Bon-Simonini reaction. After this, another reaction is Pinacol-pinacolone rearrangement. This is Pinacol. 1,2-dihydric alcohol is this. In presence of, remember, in presence of H positive. First of all, either this OH or this OH will attack this H positive and becomes OH2 positive. Suppose this attacks H positive, it becomes OH2 positive. A good leaving group, it will leave and a positive charge will be formed. When positive charge is formed over here, either this or this will shift towards this. That means this methyl will be shifted towards this. So this becomes CH3, CH3, and then it becomes CH3. After this, here it will be only one CH3 and positive charge on a carbon. But that positive charge is stabilized by back bonding. Finally, it will result in the formation of double bond O. Similarly, if you are having a structure like this, have a look. Then it is C, then after you are having like this. What will happen over here? First of all, now OH is attached to carbon which are having different groups. Remember, when OH is attached to carbon having different groups, then it is that OH which can form more stable carbocation. After protonation, it will leave as water and results in the formation of a carbocation. So that OH will attack this proton which can form more stable carbocation. Have a look. If carbocation is here, it will be more stabilized as compared to this. That's why this will attack. When this will attack, carbocation formation takes place over here. But after that, which among these will be, migrated? So that, alkyl or aryl group will be migrated, which can donate more electrons to carbocation. We know aryl can donate more electrons because of pi electron density. That's why this phenyl will be migrated over here. Hence, product formation will be like this. So phenyl will be migrated over here and it becomes like this. And here will be a positive charge and OH is attached to that. Finally, it becomes double bond O. So first, form a carbocation at that place which can form more stable carbocation. Where carbocation formed will be more stable. First that. After that, among aryl and alkyl or among different groups, migrate that group which is having more migratory power. That means which can donate its electrons more easily. That's why this is known as a reaction known as Pinacol-pinacolone rearrangement. After that, because in this case, rearrangement takes place. After this, we are having esterification. Have a look. If you are having a carboxylic acid and it reacts with an alcohol or it reacts with a phenol, then what will happen over here? It's a reversible reaction, we can say. Generally takes place in presence of HCl or H2SO4 concentrated. What will happen over here? Simple. Just break O and H bond of alcohol or phenol, and instead of that you have to add COR, that means acyl group. So it is acylation basically of alcohol or phenol. So the product formation will be R C double bond O. Instead of H of alcohol or phenol, you have to replace that H by acyl. After that, it is simply OR prime or AR plus H2O. Here oxygen came from what we call from carboxylic acid. Remember it. Say for example, this oxygen is having O18. This is O16. Then this is O18 oxygen in water. And remember, if this reaction takes place in presence of HCl only, that means esterification taking place in presence of HCl is called, that means if same reaction takes place not in presence of H2SO4, only in presence of HCl, is called Fischer-Sapir esterification. This is known as Fischer-Sapir esterification. So my dear lovely students, this is first point you have to remember, and second point you have to remember is rate of esterification. Rate of esterification is inversely proportional to size of R in RCOH. Similarly, rate of esterification is inversely proportional to size of R prime in R prime OH. That means if value of this R prime is increased, rate of esterification will decrease. Similarly, if value of this R is increased, say size of this R will be increased, then rate of esterification will decrease. That means among CH3COH and HCOH, HCOH will show esterification faster as compared to CH3COH. Similarly, among CH3OH and CH3CH2OH, CH3OH will show reaction faster. Now, let me know in the chats, quickly, let me know in the chats, let me know in the chats. Am I clear till now? Am I clear till now? Let me know in the chats. Let me know in the chats, my dear students. Okay, let me switch off some more light as there is some problem going on. Okay. Now, am I visible? Am I visible now? Am I visible now? Let me know in the chats. Am I visible now? Am I visible? Okay. Am I visible? Okay. Clear. Okay. Next is Kolbe's reaction. What is Kolbe's reaction? Have a look. If we are having a phenol, first this phenol is treated with NaOH. You will get simply sodium phenoxide. Now, upon treatment with carbon dioxide at a temperature of 400 Kelvin and at a pressure of 4 to 7 atmosphere, it will first result in the formation of this one, which upon acidification results in the formation of salicylic acid as the major product. So here salicylic acid is the major product. This is also known as carboxylation of phenol. That means addition of carbon dioxide in phenol. This is carboxylation of phenol. Have a look. Our phenol is like this. So from this to this, we have added carbon dioxide. And remember, this carbon dioxide acts as an electrophile of this reaction. This is the electrophile of this reaction, and this reaction is an example of electrophilic substitution reaction taking place generally at ortho position. After that, we have Reimer-Tiemann reaction. That means we are having a reaction of phenol with chloroform. We are having a reaction of phenol with chloroform. In presence of NaOH, approximately at a temperature of 440 Kelvin or 340 Kelvin approximately. Now, after this, NaCl will be lost and water will be lost, and first of all, it will result in the formation of an intermediate like this. CH, Cl and Cl. Then Cl will be replaced by OH. So we will get a structure like this, but we know this is not stable because two OH groups at same position, they are generally unstable. So it will lose water molecule. And results in the formation of this one, which finally abstracts a proton from acid. That means undergoes acidification and results in the formation of salicylaldehyde. Remember, this is the major product. Salicylaldehyde is the major product, and electrophile of this reaction is dichlorocarbene, and this is also an electrophilic substitution reaction. Remember one more point, you have to note down this. If CCl4 is used instead of chloroform, then salicylic acid is obtained as major product instead of salicylaldehyde, because here we get actually salicylaldehyde. Here actually we get salicylaldehyde. So if question is like this, what is the end product of Reimer-Tiemann reaction? That it is salicylaldehyde. But if question is like this, if CCl4 is used, then what will be the major product of Reimer-Tiemann reaction? At that time, it will be salicylic acid instead of salicylaldehyde. Now, am I clear till now? Am I clear till now? Am I clear till now? Let me know in the chats quickly. Am I clear till now? Let me know in the chats quickly. Let me know in the chats quickly. Okay, thank you. Thanks for, responding. Now, it's clear. Okay, great. Then after that, we are having Lieberman's nitroso test. So, remember what is this? If we are having a phenol, it undergoes electrophilic substitution on treatment with nitrous acid at para position. And this nitrous acid generally came from NaNO2 and H2SO4, and here H2SO4 acts as a dehydrating agent as well, so water will be lost and our product will be like this. It will be para-nitrosophenol. It will be para-nitrosophenol. This can undergo migration of this proton, or what we call tautomerization, and it will result in the formation of quinone oxime. This is known as quinone oxime. Now, once this quinone oxime is formed, it can react with phenol in presence of H2SO4 acting as a dehydrating agent, because this H2SO4 can act as a dehydrating agent. So it will react with quinone oxime in presence of concentrated H2SO4, which acts as a dehydrating agent. Water will be lost. Once water is lost, we will get endophenol. We will get endophenol. This is known as endophenol. This is known as endophenol. This endophenol on treatment with NaOH. Now this OH is base. This is having acidic hydrogen over here. This OH will abstract this hydrogen, so water will be lost, and we will get this one. We will get O minus Na positive. That means sodium salt of endophenol is obtained. So we will get sodium salt of endophenol. Sodium salt of endophenol. And its color is blue. And remember, with the help of this reaction, we can distinguish alcohols and phenols. Because phenols show this reaction, but alcohols do not show. So we can distinguish with the help of this reaction between alcohols and phenols. We can distinguish alcohols and phenols under the name Lieberman nitroso test. After this, we are having another reaction, that's ferric chloride test. Once again, this can be used as a distinguishing test. So we can distinguish alcohols and phenols once again with the help of this. Distinguish alcohols and phenols with the help of this reaction. Have a look. We are having a phenol C6H5OH. When treated with ferric chloride is actually Fe tripositive and Cl minus. Cl minus will abstract this H. Another Cl minus will abstract another H from another phenols. Another Cl minus will abstract another H from another phenol. That means I will write down 3 times phenol. After that, it will result in the formation of 3 times HCl plus C6H5O minus. That means phenoxide ion will be formed thrice. One from one phenol, second from second phenol, third from third phenol, and it will simply attract this Fe tripositive towards itself. So it results in the formation of ferric phenoxide. So ferric phenoxide will be obtained. Its color is generally violet. So it is violet in color. violet color compound, ferric phenoxide, is obtained. But violet color is obtained only if starting material is phenol. If starting material is alcohol, there will be no reaction like this. So there will be no violet coloration. Hence, we can simply distinguish alcohols and phenols with the help of this reaction. After this, we are having Bouveault-Blanc reduction. It is basically reduction of, it's actually or generally reduction of ester, but we can do reduction of aldehyde and ketone as well. But actually, it is reduction of ester by using sodium in alcohol. So how we perform this reduction? First of all, we break this bond and add hydrogen and hydrogen over here. After that, we break this bond, add hydrogen and hydrogen over here. That means our product will be RCH2OH, a primary alcohol, and another alcohol like this, R prime OH. This R prime depends upon the value of this R prime. This can be primary, secondary or tertiary, but this is always a primary alcohol. So this reaction, with the help of which we can reduce either aldehydes or ketones, but in general we can reduce this ester with the help of sodium and ethanol, resulting in the formation of primary alcohol, is known as Bouveault-Blanc reduction. After this, we will be having Williamson's synthesis. Have a look. Williamson's synthesis is actually a reaction of alkoxide or phenoxide. It can be sodium alkoxide, potassium alkoxide, but it is alkoxide. Similarly, sodium phenoxide or potassium phenoxide, but phenoxide. So reaction of alkoxide with alkyl halide. To differentiate this R and R, I will put a bar over here, prime over here. Similarly, a reaction of phenoxide with alkyl halide. This is a normal SN2 reaction. This is a normal SN2 reaction in which this alkoxide will act as a nucleophile, will attack electron deficient site, and X will lose. Phenoxide will attack this, or this what we call X minus will lose. So here we will get ROR prime, that means ether. Here we will get PHOR, once again an ether, and side product here will be NaX. So that reaction, during which alkoxide or phenoxide reacts with alkyl halide, resulting in the formation of ether, is known as Williamson synthesis. But remember, as it is SN2 reaction, remember this R prime cannot be tertiary or it cannot be aryl. Similarly, R cannot be what we call a tertiary alkyl, or it can never be an aryl. So aryl halides and tertiary alkyl halide do not show this sort of reaction in which ether will be formed or Williamson synthesis. They cannot show Williamson synthesis. After that, we are having Rosenmund reduction. Suppose either aryl, aromatic, or aliphatic acid chloride or acyl chloride is there. When it is treated with hydrogen in presence of Rosenmund catalyst, that means in presence of palladium with barium sulfate plus small amounts of sulfur or quinoline. This is known as Rosenmund's catalyst. Or you can use palladium calcium carbonate with small amounts of sulfur or quinoline. But this is known as Lindlar's catalyst. This is known as Rosenmund's catalyst. You can use either Rosenmund's catalyst or Lindlar's catalyst. Function is same. What is the function? Function is to convert this. You have to remove this Cl or replace this Cl by H. You have to convert this acyl halide to aldehyde. So with the help of this, we can get aldehyde. So this is Rosenmund's reduction. After that, we are having another reaction, that is Stephan reaction. What is Stephan reaction? Either aliphatic or aromatic nitriles on treatment with SnCl2HCl. Both will react, and they will react resulting in the formation of SnCl4 plus two nascent hydrogens. That means atomic hydrogens will be obtained. Those hydrogens will be simply added across carbon-carbon triple bond. That means you must have to break one bond over here, add hydrogen and hydrogen in this fashion. So you will get RCH double bond NH. That means you will get imine. After that, hydrolyze this in this fashion. Break one more pi bond and add hydrogen and hydrogen over here. So you will get This is imine, you have to hydrolyze, sorry. Now break two bonds over here, add hydrogen over here, two hydrogens over here, and two OH groups over here. As both OH are attached to same carbon, water will be lost, and here product formation will be like this. Product formation will be like this, RCHO, that means aldehyde will be obtained, plus it will be NH4 positive, which will be obtained over here. Or you will say simply NH3 plus H positive of the medium resulting in the formation of NH4 positive. But here we will get aldehyde. In nutshell, CN on treatment with SnCl2HCl followed by hydrolysis can be converted to CHO. So this is Stephan reduction. After this, we are having Itard reaction. What is Itard reaction? When you are having methyl benzene, say for example toluene, on treatment or on oxidation by using CrO2Cl2, I mean say chromyl chloride in inert solvent, it first results in the formation of a brown chromium complex. That means like this, CH, then OCrCl2OH or OCrOHCl2, one and the same, OCrCl2OH. That means you can balance the reaction like this too. So this is an unstable complex. This is brown complex or brown chromium complex. Now this upon hydrolysis gives us, have a look. Upon hydrolysis, just add hydrogen over here, OH over here, hydrogen over here, and OH over here. That means both these OH groups are present or attached to same carbon. It's not stable, it will lose water molecule, and it will result in the formation of benzaldehyde. So that reaction, with the help of which toluene gets converted to benzaldehyde by using chromyl chloride followed by hydrolysis, is known as Itard's reaction or Itard's oxidation. Now after that we are having Gattermann-Koch reaction. It's simply reaction of benzene with COHCl in presence of AlCl3 and CuCl. These all will result in the formation of this carbocation. Now, this is an electrophile of the reaction, so this electrophile will be introduced in this benzene ring, hence we will get, I mean say, benzaldehyde. So this is known as Gattermann-Koch reaction or Gattermann-Koch formaldehyde synthesis or Gattermann-Koch formylation reaction, because formyl group has been added to this. After that, we are having Gattermann aldehyde synthesis. So there is a difference, little bit difference between these two reactions here. Instead of CO, we use HCnHCl in presence of AlCl3. Now, these will react and they will form this as what we call an electrophile. After that, this electrophile is added to an aromatic ring and an imine will be obtained first. This imine upon hydrolysis will result in the formation of an aldehyde. Have a look. Both these bonds will be broken. H will be added to this and two OH groups will be added to this. But we know whenever two groups are attached to same carbon, it will lose water molecule and it will result in the formation of benzaldehyde. I hope this is clear to each and every one. Let me know in the chats. Let me know in the chats. Is this clear? Is this clear? Everyone, let me know in the chats. Am I clear till now? Am I clear till now? Let me know in the chats. Quickly. Waiting for your response, my dear students. Kirtana, thanks for replying. Rifka, thanks. Okay, Sisi, thanks. Asad, Ali, thanks. Thank you. Bhargav, thank you. Haritha, thank you. Arshi, thank you. Okay, now after this, we have another reaction, that is Clemmensen reduction. Let me tell you, this is reduction of either aldehyde or ketone. Now, what we have to do is, whenever you see zinc amalgam in acidic medium there, convert this C double bond O to CH2. That's it. That's it. This is known as Clemmensen reduction. After this, we are having Wolff-Kishner reduction. Similarly, if you are having an aldehyde or a ketone, and if this aldehyde or ketone is treated with, if this is treated with N2H4, I mean say NH2NH2 hydrazine in basic medium and in presence of high boiling solvent like ethylene glycol, then you have to convert C double bond O to CH2 and nitrogen gas will be evolved. This is what we call Wolff-Kishner reduction. So Wolff-Kishner reduction takes place in basic medium and Clemmensen reduction takes place in acidic medium. After that, we have another reaction, another reaction is Tollens test. What is meant by Tollens test? Have a look. Whether you are having aromatic or you are having aliphatic aldehyde, both can show this reaction. Whenever this is treated with Tollens reagent, whenever it's treated with Tollens reagent, these aldehydes will be oxidized and Tollens reagent will get reduced and this silver will be deposited on the walls of a test tube and will simply shine like that of a silver. That's why this is known as silver mirror. Now the question is, what is meant by Tollens reagent? This is Tollens reagent. This is, say Tollens reagent. Let me write down Tollens reagent. That is Ag, NH3, whole 2 and OH. This is known as ammonical silver nitrate. Here Ag is present in the form of Ag positive. Now it gets converted to Ag without say this positive. That means Ag0 or elemental form. So +1 to 0. That means it has simply gained 1 electron. So reduction of Tollens reagent has been taken place, but oxidation of aldehyde has been taken place. Now remember, point number 1. All aldehydes show this test. All aldehydes show this test. Number 2, alpha hydroxyketone. Only among ketones. Ketones do not show this reaction. That means we can simply distinguish aldehydes and ketones. But remember, alpha hydroxyketone can show this test. Number 3, formic acid can show this test because of presence of this, resemblance of this with aldehyde group. Number 4, hemiesters can show this test. So this can show, this can show. Number 5, N-phenylhydrazine can show this test. And all will form silver mirror. But terminal alkyne can show also this test. Terminal alkyne can also show this test. But here white precipitate will be obtained, not a silver mirror. So ketones do not show this test. With the help of this test, we can distinguish aldehyde from ketones. But remember, these all can show this test. After this Tollens test, we have another test, that is Fehling's test. And this is shown by aliphatic aldehydes only. Aromatic aldehydes do not show this reaction. After that, we treat this with Fehling's solution and this aldehyde is oxidized and Fehling's solution, in Fehling's solution, Cu di positive is reduced to CuO and its red precipitate will be obtained. What is Fehling's solution? Have a look. Fehling's solution is alkaline solution of copper sulfate containing small amount of containing some Rochelle salt, either small amounts of Rochelle salt or containing some Rochelle's salt. What is meant by Rochelle salt? Rochelle salt means sodium potassium tartrate. Remember this, my dear lovely students. Now, Fehling's solution is basically obtained. Fehling's solution is obtained basically when we add Fehling's solution B to Fehling's solution A. Actually, Fehling's solution B is alkaline solution of, it's alkaline solution of Rochelle salt, and Fehling's solution A is aqueous solution of copper sulfate. Okay. After this, we have 2,4-DNP test. Remember, if you are having an aldehyde or a ketone, but before this, let me tell you that ketones do not show this test. I mean, say only aliphatic aldehyde. Only aliphatic aldehyde shows this test. Aromatic aldehyde do not show this test. Only aliphatic aldehyde show this test. Alpha hydroxyketones can show this test, but other ketones will not show this test. And number third is formic acid can show this test. Rest of the compounds will not show this test. After this, if you are having aldehyde or a ketone and you treat this with like this, I mean to say, let me write down first in this fashion. Let me write down this reaction like this. Have a look. I will erase this one. First of all, what is 2,4-DNP? Have a look. Have a look. It is like this. 2,4-dinitrophenyl, and after that it is hydrazine. Hydrazine is basically NH2NH2. Have a look. NH2NH2 means hydrazine, but if hydrogen is removed and we will add instead of that hydrogen phenyl with 2 nitro groups at 2 and 4 position, this is known as 2,4-DNP, that means 2,4-dinitrophenyl hydrazine, also known as Brady's reagent. When this is treated with C double bond O, nucleophilic addition followed by elimination of water molecule will take place. That means here first addition, then elimination will take place, and it will result in the formation of a compound like this N, then it is NH, then it is like this, and then here it will be NO2, here it will be NO2. This product is known as 2,4-dinitrophenyl. 2,4-dinitrophenyl hydrazone. And it is 2,4-dinitrophenyl hydrazone of either aldehyde or ketone, because this is either aldehyde or ketone. That means both aldehydes and ketones show this reaction. And remember, its color is either yellow or orange or red. So with the help of this color, we can simply say whether the starting material is aldehyde or ketone. Note, in addition to aldehyde and ketone, formic acid can also show this reaction. Formic acid can also show this reaction. After this, we will be having haloform reaction. Have a look. This reaction is shown by either aldehydes or ketones having this group, or it will be shown by alcohol having this group. It will be shown by alcohol having this group. Here, R is either H or any alkyl or aryl group. Rest of the compounds will not show, this test. So among aldehydes and ketones, can I say? Among aldehydes, it's only one aldehyde which can show this test, and that is what we call acetaldehyde. Other aldehydes do not show this reaction. Similarly, among ketones, can I say methyl ketone will show this test? This can be any alkyl, this can be any aryl, but here it is methyl ketone. That means that ketone to which methyl group is attached on one side at least to C double bond O. Now, have a look. If I write down like this, it can show the test, it can show the test, but it cannot show this test, but it cannot show this test. This cannot show the test. Have a look. So, it can show the test, it will not show the test. Why? Because to C double bond O, that means to alpha position, there must be CH3. Here, it's not CH3. So, what we have to do is, when we treat this with halogen in presence of NaOH, or we simply treat with NaOX, say sodium hypohalite, there will be no reaction, no haloform formation. But here, what we have to do is just break this bond, convert alpha CH3 into CHX3 and add ONA to this, then what will be the product? CHX3, it will be a halo form, it will be precipitated out, and then HCOONA will be the product. If this X is I, then it will be iodoform, yellow precipitate will be obtained. Hence, we can simply distinguish this acetaldehyde and ethanol, and what we call this propanol or propionaldehyde. So we can distinguish acetaldehyde and propionaldehyde with the help of that yellow color, and the test will be known as iodoform test. Similarly, we can distinguish different alcohols having this group and alcohols without having this group with the help of this reaction. And if halogen taken is iodine, then test is known as iodoform test. Now, after that, we have another reaction, that is Schiff's reagent. Have a look. First of all, we will take a Schiff's dye. Schiff's dye is aqueous solution of rosanolin hydrochloride. Now, to this we pass SO2 gas. Let me tell you, this is pink in color. When we pass SO2 gas through it, it becomes Schiff's reagent and becomes colorless. And it is colorless. Now, if this Schiff's reagent is treated with aldehyde, say for example it is treated with aldehyde, then pink color is restored. But if we take ketone over here, no pink color is restored. That means ketones do not respond to this test. So with the help of this, we can distinguish, aldehydes and ketones. Let me know in the chats, am I clear till now? Let me know in the chats, am I clear till now? Am I clear till now? Let me know in the chats quickly. Let me know in the chats quickly, my dear lovely students. Let me know. Let me know in the chats, my dear students. Thank you, Aditya. Thank you, Maria. Thank you, Asad. Thank you, Rifka. Great. Thank you, everyone. Now, after this, we are having another reaction, that's aldol condensation. Let me tell you, this aldol condensation is basically of two types. One is intermolecular. And another is intramolecular. And this intermolecular is of two types. One is simple or self, and another one is mixed or crossed. Now have a look. Substrate used during this reaction will be an aldehyde. If that aldehyde contains one alpha hydrogen, then we can be having aldol reaction. That means for aldol reaction, aldehyde must contain one alpha hydrogen. But for aldol condensation, this aldehyde must contain at least two alpha hydrogens. So this reaction is shown either by aldehyde containing one or two alpha hydrogens. If only one alpha hydrogen is there, then aldol reaction will take place. But if it is having two or more than two alpha hydrogens, then aldol condensation can take place. Or we can simply say, for aldol condensation we need two alpha hydrogens from aldehyde, and for aldol reaction we need at least one alpha hydrogen from aldehyde, or we can use ketone as well. So that means this reaction is shown by either aldehydes or ketones containing at least one or two alpha hydrogens. Now, after that, the base used, reagent used during this reaction is, it is either NaOH diluted or KOH, aqueous or dilute. sometimes you can use like this Na2CO3 aqueous, or it can be BaOH whole 2 aqueous, it can be CaOH whole 2 aqueous, or it can be what we call NaOH or KOH only 10%. That means this is the reagent of this reaction. Now have a look. Let me write down first of all simple or self aldol condensation. Have a look. Very, very, very important reaction, but this is very easy. How to, remember this reaction? Have a look. First of all, there must be aldehyde or a ketone. Say for example aldehyde. There must be an aldehyde with at least alpha hydrogen. If we are performing aldol condensation, there must be at least 2 alpha hydrogens, and for aldol reaction there must be at least 1 alpha hydrogen. Next, similar type of aldehyde should be here. If you take aldehyde, then similar type of aldehyde. If you take ketone, then similar type of ketone for simple or self aldol reaction or aldol condensation. Now have a look. What you have to do is, you just show like this. Alpha hydrogen. You just write down alpha hydrogen and alpha carbon, and show alpha carbon and alpha hydrogen joined together by means of a single bond. Why? Have a look. So that we can write down a trick that this is partial positive, this is partial negative. Similarly, this is partial negative and this is partial positive. So what is the trick? What is the trick over here? Have a look. What is the trick over here? Whenever you are having a base, say for example like this, or anyone among these, now what you have to do is just replace negative and positive ions with each other, or join this positive with this negative and negative with this positive and convert double bond into single bond. So we will get a product like this: CH3CHOH, then single bond CH2, single bond C double bond O, single bond H. So this is aldehyde, this is beta hydroxyaldehyde. So this is beta hydroxyaldehyde. This is known as aldol. After that, if this aldol is heated in say medium, say base is there, if it is heated, water will be lost. Water will be lost, H will be lost from alpha, and OH will be lost from what we call beta position. Then we will get this one, CH3CH double bond CH. That means we will get a double bond between alpha and beta position. Now have a look. After that, it is like this: C double bond O and H. So I will say this is alpha beta unsaturated aldehyde. Alpha beta unsaturated aldehyde is the product. Have a look, my dear lovely students. This reaction, this reaction from this to this. Remember. I will write down this with the help of pink color. This is known as aldol reaction. After that, I will use another color. Like this. That means this one. From this to this, I will use green color now. This reaction is known as aldol condensation. Now, let me know in the chats, what is the end product of aldol reaction? That is aldol. And what is the end product of, aldol condensation? It is alpha beta unsaturated aldehyde if we start reaction with aldehyde. Or can I say aldol reaction plus dehydration of aldol is known as aldol condensation. Aldol reaction plus dehydration of aldol is known as aldol condensation. Similarly, if we take an example of ketone like this, I will show alpha hydrogen and carbon bond like this. So both are having similar structure. That means both are same, carbonyl compounds. Both are same carbonyl compounds. Then what will happen? Without heating, and in presence of NaOH, without heating, this will be negative charge, positive charge, negative charge. We have to shift this positive to negative, negative to positive, and we have to convert double bond into single bond. That means our product will be like C, it will be OH, then it is CH3, then here it will be CH2, then C double bond O, then CH3. So it is alpha, this is beta. Now this is, sorry, this is alpha, this is beta. So this is beta hydroxyketone. Beta hydroxyketone is known as ketol. But that reaction during which aldol is obtained from aldehyde or ketol is obtained from aldehyde containing at least one alpha hydrogen in presence of mild base, this reaction is known as aldol reaction. After this, if this is, say, heated, once again water will be lost. Hydrogen will be lost from alpha and OH will be lost from beta. That means there will be a double bond between alpha and beta position, and it will result in the formation of alpha beta unsaturated ketone. Now, once again, reaction from this to this is aldol, and reaction from this to this is known as aldol condensation. Reaction from this to this is known as aldol reaction. So aldol reaction plus dehydration is known as what we call aldol condensation. I hope this is clear. Now, either aldol reaction or aldol condensation takes place between similar carbonyl compounds. Hence, reaction is known as simple or self-aldol condensation. I hope this is clear. But if you want to perform aldol condensation, then its very simple trick is like this. Then you just remove oxygen of this, double bond oxygen from this, and two alpha hydrogens from this, form double bond between alpha carbon and this. That will be the product. Similarly, if you want to perform aldol condensation directly, have a look. I mean to say, if reaction is like this, CH3, I will write down like this. If reaction is like this, CH3, C double bond O, CH3. Suppose reaction is like this. As both base as well as heat is there, that means reaction is aldol reaction, and heat means loss of water, means aldol condensation will be there. So you just remember two hydrogens from alpha and oxygen from another carbonyl. Just remove that in the form of water. So you will get CH3, C, CH3, double bond. After that it is CH, then it is C double bond O, then CH3. So this is a very simple trick. Say this is alpha, this is beta, plus water is there. Now this is simple trick using, say aldol condensation in one step. This is aldol condensation in 1 and 1-2 steps. This is aldol reaction, this is aldol reaction. After that, loss of water, this is aldol condensation. So end product of aldol condensation is either alpha beta unsaturated aldehyde or alpha beta unsaturated ketone, starting from aldehyde or ketone containing at least two alpha hydrogens. But end product of aldol reaction is either ketol or aldol by reacting, ketones with at least one alpha hydrogen or aldehydes at least one alpha hydrogen. But if both aldehydes or ketones, both carbonyl compounds are same, then this is known as simple or self-intermolecular aldol condensation. I hope this is clear. Let me know in the chats, is this clear? So that I will move ahead and I will show cross-aldol as well. Now, let me know in the chats, is this clear? Is this clear till now? Let me know in the chats quickly. Let me know in the chats quickly so that I can show cross-aldol. Thank you very much. Thanks for responding. Thanks for responding. God bless you all. God bless you all. This is very, very, very important, session, as at least 4 to 5 questions will be asked in your NEET 2026 directly from this session. Now, great. After this, we will be having mixed or crossed. Mixed or crossed aldol condensation as well as aldol reaction. Have a look. Now I will show directly aldol condensation because I have shown trick of aldol reaction as well as aldol condensation. Now we can directly use aldol condensation trick. Have a look. If you are having an aldehyde with alpha hydrogens, and you are having a different aldehyde. If you are having a different aldehyde, with at least 2 alpha hydrogens as well. Now, if it is only OH minus written there, you have to form aldol here. But if heat is also there, you have to form alpha beta unsaturated aldehyde. So here 4 products will be obtained. 4 products will be obtained. Why? And which are those products? 4 products will be obtained. Have a look. First product will be obtained when this CH3 C double bond O H, that means this one, reacts with same type of molecule. I mean to say, it reacts with same type of molecule. Have a look. So 2 hydrogens from this, and say oxygen from this. So this is one of the products. So product number 1 will be CH3CH, double bond CH, single bond C, double bond O and H. So this is alpha beta unsaturated aldehyde. Both were this. Both were same. That means this is self-aldol product. Now after this, this will react like this. This will react like this with another same type of species. Have a look. Another same type of species having formula CH3CH2, CH3CH2, then it is CHO. Now this is alpha. So 2 hydrogens from alpha, then products will be like this. It will be CH3CH2, CH3CH2, then CH, then double bond, then it will be C, then here it will be CH3, here it will be CH3, it will be CHO. Now this is another product. Third product is like this. One is this, another is this. So alpha hydrogens will be removed from this one. CH3, CH2, then it will be CHO. Say 2 different products, 2 different aldehydes will combine and will give crossed product. Like this, CH3, CH, double bond, it will be C, then CH3, then it will be CHO. Have a look. Another will be, I will write down this here, that means CH3, CH2, CHO. And I will write down this one here. Say this one here, this one here. That means it will be CH3 and then C double bond OH. Have a look. So these are the 4 possibilities when both are having alpha hydrogen. So water will be lost. Everywhere water will be lost, and the product will be CH3, CH2, CH, double bond CH, single bond C, double bond OH. So 4 products will be formed. Now the question is, which one will be major? Remember, major will be that one from which 2 alpha hydrogens will be lost. 2 alpha hydrogens should be lost from least reactive carbonyl compound. Least reactive during nucleophilic addition reaction. We know among these 2, this is least reactive as compared to this. Least reactive means to which strong electron donating group is attached. Ethyl is strong electron donating as compared to methyl. So to that carbonyl to which more electron donating group is attached, remember that is least reactive. So you have to lost 2 hydrogens from least reactive, that means CH3, CH2OH. That means either this or this, because both are least reactive, so 2 alpha hydrogens should be lost from them. Now after that, second one, you have to lose O from most reactive aldehyde or most reactive carbonyl compound but most reactive during NAR, I mean say nucleophilic addition reaction. So this is ethanol, this is more reactive. That means you have to lose O from this and you have to lose 2 hydrogens from this. That means it will be this one. This one will be the major product. So this one will be the major product. Here this is, I mean say least reactive, but this is same. This is also least reactive. So hydrogen should be lost from least reactive and oxygen should be lost from most reactive. So this is what we call cross-aldol condensation. But if OH minus is there, heat is not there, then you have to form aldol products. Here, here, here and here. Then 4 aldol products will be formed. I hope this is clear to each and every one. Let me know in the chats, is this clear? Now, can you find out the major product during aldol or cross-aldol condensation? Can you find out the major product during your examination? Because now it's very easy. You have to remove 2 alpha hydrogens from least reactive and you have to, I mean say, remove oxygen from most reactive aldehyde or ketone. Now, okay, this is clear. After that, sometimes it is like this. Sometimes you are having a reaction like this. Sometimes you are having a reaction like this. You are having an aldehyde like this and you are having an aldehyde like this. Sometimes it's like this. Now, have a look. If you treat this and this in presence of base, have a look. Not heat. What will form? What will be formed over here? What is the trick? I mean say aldol, what is the trick of aldol? Let me write down this in this fashion so that you can, I mean say, remember that trick always. This is alpha. So this is having partial negative, this is having partial positive, this is having partial positive, partial negative. First of all, convert this into single bond, give this H positive to this, that means it will become this. After that it is CH2, then it is C double bond O and H. Have a look. Can I say this is alpha? Can I say this is beta? Can I say this is gamma? So whenever you are having an aldol in which gamma position contains a double bond. Because if you write down the resonating structure of this, then here it is a double bond. Whenever your aldol contains or ketol contains a double bond at gamma position, remember without heating it will undergo. Alpha, beta, I mean say it will undergo aldol condensation. That means without heating it will lose water molecule. Otherwise it will not lose water until and unless it is aldol is heated or ketol is heated. But if aldol or ketol contains a double bond at gamma position, it undergoes dehydration and it will result in the formation of this one. Let me write down over here resonating structure so that you can understand much more over here. So I mean to say, if we are having a double bond at gamma position, then it will result in the formation of this one. OH will be lost from beta, H will be lost from alpha, and we will get this one. Now the question is, why no heat is, I mean say, necessary for this dehydration? Because when you are having double bond at gamma, when you lose water molecule, there will be alpha beta double bond as well. So this double bond and this double bond, there will be extended conjugation. Molecule becomes very much stable. So because of extended conjugation, no heat is required over here. Without heating, it will undergo aldol condensation. But if there is no double bond at gamma position of aldol or ketol, there will be no aldol condensation. There will be no loss of water until and unless heat is there. So this is all about what we call cross-aldol condensation. After that, last point of this aldol is intramolecular aldol condensation. Intramolecular aldol condensation. Have a Have a look. If you are having this one, CHO, then CH2, then CH2, like this. Can I say this is alpha with respect to this? So remove two hydrogens from alpha position and remove oxygen from another, I mean say C double bond O, if aldol condensation takes place. I mean say if this is heated with OH minus, you have to remove this two hydrogens from this position, that means from first position, suppose this one, then this is second, then this is third, then this is fourth, then this is fifth. That means you have to combine carbon number 1 and carbon number 5. Now, it's not the numbering of nomenclature, it is simply which carbon has to combine with which carbon. So you have to combine carbon number 1 and carbon number 5. Have a look. When you combine carbon 1 and carbon 5, there will be a 5-membered ring. Suppose this is carbon number 1. If this is carbon number 1, at carbon number 1 we are having CHO group. Then carbon number 2, let us suppose this is carbon number 2 because 1 is attached to 2, 2 is attached to 3, 3 is attached to 4, 4 is attached to 5. Now 5 is attached to 1, but at 5 double bond has been lost. At alpha position, I mean say at 1 hydrogen has been, 2 hydrogens have been lost. Have a look. 2 hydrogen has been lost. Then this, I mean say alpha hydrogen forms 1, 2 bond. That means this carbon, alpha carbon, this one carbon, it forms another bond over here. So 2 hydrogens will be lost. So 1, 2 and 3 and 1 hydrogen will be there. That means, have a look, have a look, have a look. 2 hydrogens will be lost. That means there will be a double bond between 1 and 5. There will be a double bond between 1 and 5. There will be a double bond between 1 and 5. 1, 2, 3, 4. Because when alpha, yani carbon 1 will lose 2 hydrogen and this carbon 5 will lose 2 hydrogen, there will be a double bond between that. So this was alpha, this is beta. So can I say this is beta, alpha beta unsaturated aldehyde known as aldol condensation. But remember, as it results in the formation of ring, that's why during this either 5 or 6-membered ring should be formed. But if it is aldol reaction, if heat is not there, then what we have to do is you have not form this double bond, you have to form OH over here. Then after heating, H will lost from this, OH will lost from this. In nutshell, there will be alpha beta unsaturated aldehyde or alpha beta unsaturated ketone depending upon these structures. Now, after this, I hope this is very much clear to you. Now, next is Claisen condensation or sorry, Claisen-Schmidt condensation. Now, what is this? Have a look. Whenever you are having an aromatic aldehyde without alpha hydrogen, whenever you are having an aromatic aldehyde without alpha hydrogen, and it is treated with aliphatic aldehyde with at least 2 alpha hydrogens or aliphatic ketone with at least 2 alpha hydrogen or with aliphatic ester with at least 2 alpha hydrogens. So whenever aromatic aldehyde without alpha hydrogen is treated with aliphatic aldehyde or aliphatic ketone or aliphatic ester containing at least 2 alpha hydrogens in presence of mild base, there will be a condensation. There will be a condensation reaction. Heat is not necessary because it will result in the formation of a sort of aldol which is having, I mean say, double bond at gamma position. Similarly over here. Finally, what will be the product? You just remove water molecule. It will result in the formation of alpha beta unsaturated aldehyde. Here, end product will be alpha beta unsaturated ketone. Here, product will be alpha beta unsaturated ester. So remember that reaction during which Aromatic aldehyde without alpha hydrogen reacts with aliphatic aldehyde or aliphatic ketone or aliphatic ester containing at least 2 alpha hydrogens in presence of base, resulting in the formation of either alpha beta unsaturated aldehyde or alpha beta unsaturated ketone or alpha beta unsaturated ester. Reaction is known as Claisen-Schmidt condensation. After that, Perkin condensation. What is meant by Perkin condensation? Perkin condensation means whenever you are having an aromatic aldehyde without alpha hydrogen and it reacts with aliphatic acid anhydride, aliphatic acid anhydride containing at least 2 alpha hydrogens. Same type of reaction takes place in presence of sodium salt of acid from which this anhydride has been obtained at a temperature of 453 Kelvin. Water will be lost and it will result in the formation of a condensation product first. So this is the condensation product formed over here. This is the condensation product. But at the very same time, water is there. Now this water will simply hydrolyze this. That means we have to break down this, then hydrogen will go here and OH will go here, and finally we will get alpha beta unsaturated carboxylic acid. This reaction in which we get alpha beta unsaturated acid from aromatic aldehyde and aliphatic without alpha hydrogen and aliphatic acid anhydride containing at least 2 alpha hydrogens is known as Perkin condensation. Am I clear till now? Let me know in the chats. Am I clear till now? Am I clear till now? Let me know in the chats. Am I clear till now? Am I clear till now? Let me know in the chats, guys. Thank you, thank you, thank you. Okay. Then next reaction is benzoin condensation. What is benzoin condensation? Self-condensation of aldehyde known as benzaldehyde. So it is self-condensation of benzaldehyde. It is self-condensation of benzaldehyde in presence of alcoholic potassium cyanide. What we have to do is, first of all, we have to break CO bond into a single bond and give this hydrogen to this. Give this hydrogen to this oxygen. First of all, double bond breaks and it becomes CO minus. O minus will, abstract this H positive. Then this C minus will form bond with this. That means it will form like this. Bond formation will take place over this. This is ketone. This is hydroxy. So this is alpha hydroxy ketone. Alpha hydroxy ketone obtained by self-condensation of benzaldehyde is known as benzoin. And this condensation is known as benzoin condensation. After that, we are having Claisen condensation. Have a look. Claisen condensation means self-condensation of aliphatic ester. Self-condensation of aliphatic ester containing at least, let me write down over here CH3 directly. So aliphatic ester containing at least 1 alpha hydrogen, So self-condensation of ester containing at least 1 alpha hydrogen. What we have to do is just break this bond. Then it becomes ETO minus, that will abstract this hydrogen. So it becomes ETOH. Have a look. It becomes, and reaction takes place in presence of sodium alkoxide. So this and this both will react and they will result in the formation of ETOH. This alpha will form bond with this. That means we will get this one. And here main functional group is ester. So this is alpha, this is beta. I mean to say end product of this reaction is beta keto ester. This is Claisen condensation. That former one was Claisen-Schmidt condensation. This is the difference. So in Claisen condensation, beta keto ester is the end product. After that, we are having Cannizzaro reaction. Once again, Cannizzaro reaction is either of two types. It's either of two types, intermolecular, and second is what we call intramolecular. Intermolecular is of two types. One is simple or self, and another is mixed or crossed. Another is mixed or crossed. Have a look. Let me show you first simple or self, intermolecular, Cannizzaro reaction. Have a look, my dear lovely students, have a look. Have a look, dear students, have a look. This reaction is an example of, or this reaction is disproportionation reaction. That means this is self-oxidation as well as reduction. So this is disproportionation reaction. This is disproportionation reaction. Yani self-oxidation and reduction will take place. Have a look. If you are having, first of all, this reaction, next point, this Cannizzaro reaction, let me tell you, is shown by aldehydes only. Aldehydes only without acidic hydrogen or without alpha hydrogen. Without alpha hydrogen. So this is shown by aldehydes only, that too without alpha hydrogen. So I will write down a reaction like this. Formaldehyde. Now I will take another same type of molecule, because whenever similar aldehyde molecules without acidic hydrogen undergoes reaction, we can call that as self or simple intermolecular this Cannizzaro reaction. Now here reaction takes place in presence of NaOH or KOH, generally concentrated, or 50% NaOH or KOH. Now what will happen? One molecule will oxidize, another molecule will reduce. How? Just convert one CHO into COONA. COONA, that means it is oxidized. Convert this one. Convert C double bond O. Convert C double bond O of another into CHOH. That means convert another C double bond O into CHOH. That means we have broken this C double bond O bond into C single bond O. Then we have add hydrogen and hydrogen over here. So addition of hydrogen means reduction. And here we have added what we call oxygen, or we have converted this aldehyde to acid or H sodium salt. So this is oxidized, this is reduced. Now, similarly, if we are having this example, benzaldehyde, another is also benzaldehyde, that means same type of molecules are there. So one will be oxidized, another will be reduced. That means self-oxidation reduction takes place. That means one will be converted to COONA from CHO. Another C double bond O will be converted to CHOH. So it is CHOH. This is also H. So can I write down like this? It becomes CH2OH. So one is converted to sodium salt of acid, another is converted to alcohol. So this is oxidized, this is reduced. So can we say same benzaldehyde is oxidized, benzaldehyde is reduced. That's why this is known as self-oxidation reduction, known as disproportionation. But if we are having mixed or crossed, if we are having mixed or crossed Cannizzaro, or mixed or crossed intermolecular Cannizzaro reaction, then what will happen? That means now different aldehydes will take part in this reaction, but remember both aldehydes must not have any alpha hydrogen. I mean to say, if one is having formaldehyde, one is formaldehyde and another is benzaldehyde, neither of them should have alpha hydrogen. If one is having alpha hydrogen, then it will undergo what we call Crossed-aldol reaction, not crossed Cannizzaro reaction. So for Cannizzaro reaction, neither of these have alpha hydrogen. So this is not having alpha hydrogen, this is not having alpha hydrogen, then we can simply think about Cannizzaro, cross Cannizzaro. Now, have a look. This is CHO, this is CHO. Listen carefully. To this CHO, this benzene ring can donate electron, but here no say such atom is attached to aldehyde which can donate electron. Any which donates electron, or if aldehyde group is attached to electron donating group, that becomes least reactive. So remember, this is least reactive or less reactive among these two. This is less reactive among these two. This is less reactive towards nucleophilic addition. Less reactive towards nucleophilic addition reaction. And this is more reactive towards nucleophilic addition. Towards nucleophilic addition reaction. And remember, you have to oxidize most reactive and you have to reduce less reactive. That means you have to add H and H over here across C double bond O, and you have to convert this into CONA. So the product of this reaction will be like this. So the product will be like this. This becomes CHOH and H is also there. So this will become, product will become like this. Similarly, if you are having, have a look, if you are having this one, that means benzaldehyde, and another is like this. This is benzaldehyde, but NO2 group is attached. Now this becomes electron withdrawing. If it is electron withdrawing, this is electron donating. This becomes less reactive, this is more reactive. So this is less reactive, this is more reactive. So less reactive is reduced and more reactive is oxidized. So here product of the reaction will be less reactive is what we call reduced, more reactive is oxidized. So the product of this reaction will be like this. It will become CH2OH plus it will become NO2. Here it will become C double bond O, ONA. So this is oxidized, more reactive is oxidized, more reactive is oxidized, and less reactive is reduced. I hope this is clear to each and every one. After that, we are having Tischenko reaction. Remember, all types of aldehydes show this reaction. All types of aldehydes show this reaction. What is meant by all types of aldehydes show this reaction? I mean to say, aldehydes with alpha hydrogen or aldehydes without alpha hydrogen can show this reaction. Say for example, if I write down this one, CH3CHO, CH3CHO, same type of aldehyde. Now in presence of aluminium ethoxide, one aldehyde is oxidized to carboxylic acid, another is reduced to alcohol. So can I write down like this? So it becomes COOH, say oxidized, but not into sodium salt, into carboxylic acid, and this become reduced. That means C double bond O becomes CHOH. This is also H. That means this is CH2OH. Can I write CH2OH like this? And then it is CH3. That means almost same type of what we call Cannizzaro reaction takes place. Now here, water will be lost. OH from carboxylic acid and H from alcohol, and finally it will result in the formation of ester. So that reaction during which aldehydes with or without alpha hydrogen results in the formation of ester, but first results in the formation of one carboxylic acid and one alcohol. That means one aldehyde is oxidized to carboxylic acid, another is reduced to alcohol. After that, they will lose water and results in the formation of ester in presence of aluminium ethoxide. This type of reaction is known as Tischenko reaction. Another reaction is HVZ reaction. So let me tell you that this reaction is shown by carboxylic acids containing at least one alpha hydrogen. For example, if you are having this one, CH3COOH, so this is having alpha hydrogen. When halogenation of this takes place in presence of red phosphorus and followed by hydrolysis, then what will happen? hydrogen is replaced from alpha hydrogen by halogen, but remember halogen here is either chlorine or bromine. Now that means here chlorination will take place at alpha position or bromination will take place at alpha position. So this is known as what we call Hell-Volhard-Zelinsky or reaction. This is Hell-Volhard-Zelinsky or Zelinsky reaction. In short, this is known as HVZ reaction. Now if, say for example, X2 is taken in excess, then all these hydrogens will be replaced by halogen. So this is halogenation generally taking place at alpha position, but in halogenation it is either chlorination or bromination generally taking place at alpha position. After this, we will be having Hofmann's ozonolysis method. Have a look. If we are having an alkyl halide and we treat it with ammonia, now what will happen? This X will be replaced by NH2. That means H of NH3 and X of this alkyl halide will be lost and we will get a primary amine. We will get a primary amine. But if alkyl halide is taken in excess, then X of alkyl halide and H from this primary amine will be lost in the form of HX. We will get RNHR, that means we will get a secondary amine. Now, after that, if alkyl halide is taken in excess, once again H from nitrogen, that means from amine, and X from alkyl halide will be lost. We will get a tertiary amine. In these reactions, amine will act as a nucleophile and Rx will act as an electrophile. Finally, this lone pair will attack this and X minus will be lost. So we will get R3 and this R4, N positive and X minus. This is known as quaternary ammonium salt. So whenever alkyl halide is treated with ammonia, resulting in the formation of quaternary ammonium salt via formation of primary amine, secondary amine and tertiary amine, reaction is known as Hofmann's ozonolysis method, and this reaction is generally SN2 if this R is 1 degree. And this is generally what we call SN1 reaction if this R is, I mean to say, tertiary. Now, after this, we have another reaction, that is Zinin reduction. Remember, this is a selective reaction. This is a selective reduction. This is a selective reduction of nitro compounds. Have a look. If we are having more than one nitro group present in benzene ring, and these are treated with either sulfides or polysulfides, say for example ammonium sulfide or sodium sulfide or sodium disulfide, I mean say sulfides or polysulfides, then the function of these sulfides or polysulfides is that they will reduce one of the nitro groups only and they will not affect another nitro group. Say for example, they will reduce one NO2 to NH2 and another will remain unaffected. This is known as selective reduction. That means selective reduction of this takes place or selective reduction of this takes place. So among these two, only one will be reduced to NH2. This is known as Zinin reduction. After this, we will be having Mendius reduction. Now the question is, what is meant by Mendius reduction? If we are having cyanide, whether it is sodium, I mean say alkyl or it is aryl, this upon reduction by using sodium amalgam or sodium in ethanol, it's either sodium in ethanol or sodium amalgam in ethanol. What we have to do is we have to break these bonds, add hydrogens over here and add hydrogens over here. That means addition of hydrogen will take place and it will result in the formation of a primary amine. So we simply convert this cyanide to CH2NH2. This is known as primary amine. So whenever cyanide is converted to CH2NH2, reduction of cyanide takes place by using sodium in ethanol or sodium amalgam in ethanol. This reaction is known as Mendius reduction. After this, we will be having Gabriel thalamide synthesis. Have a look. What is this? This is known as thalamide. This is known as thalamide. This is known as thalamide. This is thalamide. Now, this upon treatment with base, say for example KOH, O minus H positive, base will abstract this H positive. That means it will result in the formation of potassium thalamide. It will result in the formation of potassium thalamide. After this will react with Rx. Let me write down what is R. R is either alkyl. Generally, R is not the tertiary alkyl. R can never be an aryl. So R is an alkyl, or R can be like this. That means a benzyl group. So it can be like this. So it can be either alkyl or benzyl, but it can never be a tertiary alkyl, or it can never be an aryl, because this is an SN2 reaction. It will attack over here, X will lost. That means KX will be lost over here. After that, it will result in the formation of this one. C double bond O, then it is N attached to R, then it is C double bond O attached to R. After this, you can simply hydrolyze this. Now have a look. If hydrolysis takes place, give H to this, OH to this. Give H to this, OH to this. That means we will get a primary amine during this reaction. We will get RNH2, means primary amine during this reaction. So primary amine is obtained during this reaction, plus you will get a phthalic acid over here, COOH. But remember, if this hydrolysis takes place in basic medium, that means a base is there, then this acid will be converted to salt. Say for example, if it takes place in presence of NaOH, then this becomes CONA. That means sodium salt of phthalic acid. But primary amine will be obtained. Okay. After this, we will be having Hofmann's bromamide degradation. Let me tell you, this is also known as Hofmann's bromamide reaction, or this is also known as Hofmann's rearrangement. Hofmann's rearrangement. Now, have a look. What is this? This is actually an aromatic or aliphatic amide. When treated with, remember forever, when treated with Br2NaOH or Br2KOH or NaOBr, sodium hypobromite, or KOBr, potassium hypobromite. This is O. Okay. Then what you have to do is just remove this C double bond O. That means we will get an amine with one carbon lesser than that of parent amide. One carbon in amine, primary amine, is less than that of parent amide. But you have to remember, this bromine is taken as 1 mole, and this sodium hydroxide or potassium hydroxide, 4 moles of this will be used. I mean to say, you can write down this reaction in this fashion. ArRCONH2 plus Br2 plus NaOH, but this is 4 times, this is 1, that means this is having 4 moles. Then we will get Ar or RNH2, that means primary amine, whether it is aliphatic or aromatic, plus it will be Na2CO3 plus it will be twice NaBr plus twice water. So in this fashion, oxygen 2 and 3, 5. Here 1 and 4, 5 oxygens are balanced. Hydrogen 4, 4 and 2, 6. Here it's 2, 2 and 4, 6. Hydrogen balance. Sodium 4, sodium 4 balance. Similarly, bromine 2, bromine 2 balance. Each and everything is balanced. If you write 4 times KOH, then it is K2CO3 and twice KBr. Okay. Now, this reaction, with the help of which amide is converted to primary amine, but with 1 carbon lesser than, in this 1 carbon is lesser than what we call parent amide, on treatment with either of these is known as Hofmann's bromamide reaction or Hofmann degradation reaction. But the important thing is that this is rearrangement reaction and intermediates intermediates of this reaction is, first intermediate, you must remember this, is RCO NHBr, N-bromamide. Second intermediate you can say is RC double bond O N. This is known as acyl nitrene. And third will form like this. This will form a double bond over here and R will shift over here. That means R will form bond with N. N forms double bond with C. C is having double bond with O. This is alkyl isocyanate. So these are the intermediates of this reaction. After that, another is Schotten-Baumann reaction. What is Schotten-Baumann reaction? It is simply benzoylation of any acidic hydrogen containing compound, say for example phenol, say for example aniline, because they can lose H positive, hence they are acids. So acidic hydrogen containing compound, benzoylation. So benzoylation of any acidic hydrogen containing compound, benzoylation of any acidic hydrogen containing compound in presence of NaOH in general, in presence of NaOH in general, what will happen? What will happen? It will simply form this C double bond O and this. That means this is an ester. So this is simply an ester. So ester formation will take place over here. Here it will ester formation, here it will be amide formation. NH, C double bond O and then this. In nutshell, what we have to do here is that we have removed or replaced this H by benzoyl group. So this is benzoylation of phenol. Here we have replaced this H by benzoyl group. So this is benzoylation of aniline. So benzoylation of any acidic hydrogen containing compound, any acidic hydrogen containing compound by using benzoyl chloride. This is known as benzoyl chloride. So by using benzoyl chloride in presence of NaOH in general, in presence of NaOH is called Schotten-Baumann reaction. So this is one of the examples of Schotten-Baumann. This is another example of Schotten-Baumann. So this is known as Schotten-Baumann reaction. After this, but before starting this, let me know in the chats, am I clear till now? Let me know in the chats, am I clear till now? Am I clear till now? Quickly, let me know in the chats quickly. Let me know in the chats quickly. Am I clear till now? Am I clear till now? Because we have to complete each and every named reaction. Thank you, Kirtana. Thanks for replying. What about others? What about others? Okay, Asiba, thank you. Rivka, thank you. Maria, thank you. What about others? What about others? Okay, thank you, Asiba, thank you. Thank you. God bless you. Okay, thank you, Bhargav. Okay. After that, we are having a carbyl amine reaction. Very, very important reaction. Whenever you are having an aromatic or aliphatic primary amine. Aromatic or aliphatic primary amine. On treatment with chloroform and KOH, alcoholic, results in the formation of isocyanide carbyl amine or isonitrile. Isocyanide carbyl amine or isonitrile is formed and its smell is very unpleasant. So it's having unpleasant odor or bad smell or foul smell. So this reaction, with the help of this smell, we can simply distinguish, that means primary amine from rest of the amines. Hence this is used as a distinguishing test. So we can use it to distinguish primary amines from rest of the amines. That means we can distinguish primary amines from rest of the amines with the help of this reaction, and this test will be known as carbyl amine test or isocyanide test or isonitrile test. I hope this is clear. After that, we are having Hoffman's mustard oil reaction. What is this? This is reaction of aliphatic primary amine. Only aliphatic, not aromatic. Aliphatic primary amine. Before, in this reaction,